Hi everyone. In this video we're going to take a look at molecular geometry. Now this is one of the important steps in trying to figure out how structure affects the properties of molecules. So far we've already covered looking at Lewis diagrams. We're going to be using those Lewis diagrams in order to try to figure out the molecular geometry. We're going to be using molecular geometry to figure out whether molecules are polar or nonpolar. And it is that molecular polarity that really helps to determine the properties of molecules. So, molecular geometry uses what's known as the VSEPR model, which stands for the valence shell electron pair repulsion. Bottom line is that this is just going to take a look at trying to minimize electron repulsions around the central atom. It's the valence electrons around the central atom that's going to determine the shape of the molecule. We're going to break those valence electrons into two different groups. We're going to have unshared pairs, which show up as a pair of dots in the Lewis dot diagrams, and we're going to look at shared pairs, which are going to be bonds to the central atom. Now when we take a look at the shared pairs, sometimes you'll notice in your Lewis dot diagrams that you get double or triple bonds, but these areas are not able to separate from themselves, and so they're going to count as just one electron area, and so really just count those as one pair, even though it'll be a bigger pair. So, how do we put this into action? Here are the steps to follow. You start off by drawing the Lewis dot diagram for your example. You identify on the central atom the bonding and non-bonding pairs. And once you get the total for that, that's going to determine the shape that you're going to have. The best way to start to become comfortable with the VSEPR model is to start working through some examples. We're going to start off by looking at examples that involve only bonding pairs, and there'll be no unshared pairs on the central atom. In our first example, let's take a look at beryllium difluoride. Beryllium's in group 2, so that'll bring 2 valence electrons. Fluorine's in group 7, and there are 14 valence electrons because we have 2 of those. And so that gives us 16 electrons to work with. The single atom beryllium will go in the center, and that'll give me 2 bonds to the fluorines, which will use up 4 electrons. The 12 electrons that remain will have 6 electrons around each of the fluorine atoms. As we turn our attention to the central atom beryllium, we notice that beryllium does not have an octet, but that's okay because beryllium is an exception and needs to be surrounded by 4 valence electrons. So this would be the final structure. And now let's start taking a look at applying the VSEPR model. For the VSEPR model, we only look around the central atom, beryllium, and so we can see that for bonding areas, what we have is beryllium is bonded to 2 different atoms. For unshared pairs or lone pairs, we don't have any, and so the total number of electron areas that we have is going to be 2. And in order to get 2 electron areas as far apart as possible, we're going to put them 180 degrees apart, just like it's implied with the diagram, and the name for this shape is linear. Alright, let's erase this and we'll start a new example. Let's continue by doing boron trifluoride, or BF3. First we'll do the Lewis structure for this one, and that is going to come out to have boron in the center with 3 fluorines around. We've practiced a lot of Lewis dot diagrams so far, so I'm just going to skip to the answers from here on. And taking a look around the central atom, boron, we notice that there are 3 bonding areas. I'll make a little table here. So for bonding areas we have 3. Lone pairs on the central atom only we have 0. So that gives us a total of 3 electron areas around the central atom. The best way to get 3 electron areas as far apart as possible is to have them all in the same plane, 120 degrees apart. So the angle that we have right here would be 120 degrees. And we can tell that it's 120 degrees apart because if you do a full lap around the circle, that would be 360 degrees, and so 1/3 of the way would be 120 degrees. The name for this shape happens to be a trigonal planar. Oh, I didn't leave myself enough room. There we go. Alright, let's try a new example. First, let's erase what we have. For our next example, we'll take a look at methane. Methane has the formula of CH4. For the Lewis structure, it's very simple. We just have carbon in the center attached to 4 hydrogens. And for the little table that we can make up here for the total electron areas, the bonding electron areas, and the lone pairs, when we look at the central atom, carbon has 4 bonding areas. There are no lone pairs, and so that'll give us a total of 4 electron areas. Now you might expect that the way to get 4 electron areas as far apart as possible is to have them all lie in the same plane and be 90 degrees apart. In other words, you kind of have more of like a square planar. But the shape for this one actually turns out to be what's known as a tetrahedron, which is a 3-dimensional structure. I'm sure many people aren't that familiar with the tetrahedron, so let's look at the structure of what that would look like. You can see that it has a triangular base to it, and this is a triangular pyramid all composed of equilateral triangles. The bond angles here, from there to there, would be 109.5 degrees, and so you can see that that would be a little bit better than working with a flat structure. So we have 2 examples left. Let's continue on by clearing some room for ourselves. And our next example is going to be PCl5, or phosphorus pentachloride. Again, we'll kind of skip right ahead to looking at the Lewis structure. And so we'll have phosphorus in the center surrounded by the 5 chlorines. Once you've taken into account where all the electrons go, all the chlorines will have 6 electrons around them. And this is an example where phosphorus had the expanded octet. So we have 5 bonding areas. We do not have any lone pairs on the central atom, and so that gives us a total of 5 electron areas. In order to get 5 electron areas as far apart as possible, we're going to adopt a trigonal bipyramid structure. So we'll need to take a look to see what a trigonal bipyramid looks like so we can understand that a little bit better. So here's a model for one. You can see that there's a triangle in the center, and that'll form the base of a pyramid going upwards and the base of a pyramid going downwards. A lot of different bond angles that are present in here. You can see from, if you go from the top to the center to the bottom, that's 180 degrees. If you go from the top to the center to one of the sides, it'd be 90 degrees. And then within that central plane there, which is called the equatorial plane, the angles are 120 degrees. So let's get ready for our last example by cleaning up our diagram. And our last example is going to be sulfur hexafluoride, which has a formula of SF6. In that structure, sulfur goes in the center, and it's surrounded by the fluorines. And each of the fluorines will get 6 valence electrons added to get it up to an octet. So in the end, for total electron areas, we're going to have 6, where 6 of those are bonding, and we do not have any lone pairs on the central atom. This structure has an octahedral shape to it. And I would like to go through and show you what that looks like right now. And there it is. What you can see is that equatorial plane, that plane in the center, is shaped like a square, and so you'll have a square pyramid going up and a square pyramid going down. And instead of calling this a square bipyramid, what they went with is how many sides are exposed. And if you imagine one of the Great Pyramids in Egypt, you could clearly see that there would be 4 sides exposed, and so there's going to be 4 sides exposed on the top, 4 sides exposed on the bottom, and that gives you 8 total sides, and that's what the name octahedral means. For bond angles, if you go from the top to the center to the bottom, you can see that would be 180 degrees. Top to center to one of the sides is going to be 90 degrees. So there are 2 bond angles present for this example. So let's review what we've learned so far. In the VSEPR model, what we want to try to do is we want to try to reduce electron repulsions by moving the electron areas around the central atom as far away as possible. When we have all bonding pairs, it's going to lead to this series of shapes. Now in our next video, part 2, we're going to take a look at what happens when we also have unchaired pairs on the central atom. And you're going to see that the shapes are derived from these 5 shapes here.